Yeah, okay. Okay, so the aim of my talk introduce new class of algebras, which are called generalized Weyl algebras. This is one class, and another class is diskew polynomial rings. So there are kind of all generalized Weyl algebras. They, roughly speaking, I will talk about only rank 1 algebras. There are generalization for arbitrary rank, but it's too involved to explain in this talk. So all generalized Weyl algebras were introduced 30 years ago, and it depends on single automorphism, arbitrary ring, single automorphism, and arbitrary element of the center. The new generalized Weyl algebras I'm going to explain of rank 1, instead of one automorphism, we have two automorphisms. And the element of the center can be arbitrary element of the ring. And diskew polynomial ring are completely new kind of objects. And roughly speaking, this is example, if you start with arbitrary ring, this is example of two-step iterated OR extensions. Iterated OR extensions are very complicated objects, and even two steps are very complicated ones. Okay, so what I am going to do, I will give a definition, we will consider examples, and I will give simplicity criteria for this class of algebras. So if you have any question during my talk, interrupt me on the spot. Okay, so let me recall the old definition of generalized Weyl algebras. So we start with arbitrary ring D, arbitrary automorphism, and the elements of the center. Then the generalized Weyl algebra is produced from this ring D by adding two variables, x and y. And we use this definition. And subject to these relations. So when element of the ground ring is moved to the left, it is twisted by sigma. And when D is moved to the left, it twisted by sigma minus 1. For all elements of D. And these two elements meet, they produce the central elements of D, it should be D, sorry. And when they meet in the opposite way, it produces sigma A. So the generalization I am going to introduce, first of all, this sigma minus 1 will be replaced by arbitrary another automorphism or endomorphism. So many classical algebras, this is a purely experimental fact, very old one, that many classical algebras are example of generalized Weyl algebra. So I will give several examples of this, like Weyl algebra, quantum plane, quantum sphere, UQ SL2, and Witten-Voronovich deformation. So it means when usually this ring is a polynomial ring in one or two variables, and this in all this classical example. And sigma is simply very trivial affine automorphism, and element A, it's a usually quadratic element. So when instead of these trivial automorphisms, affine automorphisms, you will take some other automorphism. For example, polynomial ring in two variables has a huge group of automorphism, and the affine part is a very small one. So instead of this automorphism sigma, you produce arbitrary automorphism, and instead of element A, which is usually quadratic, it has a connection with the Casimir element, you take arbitrary element, you will produce kind of generalization of this classical result straight away. So let me give a flavor of these presentations for classical algebras. So the name came from Weyl algebras. And the presentation as a generalized Weyl algebra is the following one. So we have two canonical generators. The commutator is equal 1. Then if you want to express the Weyl algebra as a generalized Weyl algebra, so you have to choose the ring, which is simply polynomial ring in one variable h. So you have to choose automorphism. So this is shift. And you have to choose the element, which is h. Now, of course, and this is basically presentation which gave the name for this class. So this is a differential operators on the line. So when we start to commute, when you use differential operators, the difficult problem, especially for kind of, if you're interested in computation and multiplicative property of these algebras, the difficulty is when you start to make any computation, it explodes. But presentation of your object as a generalized Weyl algebra, it's a very easy to multiply element. So your elements, so coefficients shifted by this automorphism, and that's it. So that is why also as a computational tool, it's a very, as soon as you have found presentation, you can do many things straight away. Now the quantum plane, this is generated by x, y, and this relation. So what do we have to do if you want to represent as a generalized Weyl algebra? So the ring is the same, the element is the same, the automorphism instead of shift, we take q. So it means from this point of view, quantum plane and Weyl algebra are simply the same object. So now when you look at the UQSL2, it is generated by these elements, subject to these relations. So what about the presentation? So you have to choose the base ring. So the base ring is a localization of the polynomial ring in two variables at the powers of h. So automorphism you can guess. Simply very trivial automorphism, simply multiplication by q, and c is sigma invariant, and element A is rather complicated element, but c is a Casimir. So the general idea, if you know the Casimir of your classical object and you suspect that this will be a generalized Weyl algebra, so Casimir gives you this element A. Because what is A? This is yx. So when you move this polynomial to the right, to the left, and represent A as a yx, so this gives you the Casimir and vice versa. Okay, so maybe I will not spend much time on presentation Voronovich and Witten, so maybe very quickly. So Witten's deformation is this, generated by three variables, kind of quadratic relations. So presentations, polynomial ring in two variables. Automorphism is very not that sophisticated automorphism, and element A simply V. And similar story with two Witten's deformation. So these are generators. These are kind of quadratic relations. And again, so we start with the Casimir C. So this is a central element. And your element A here, this is simply C minus this element. And the automorphism is simply affine automorphism. And similar story for other, slightly more involved presentation of this quantum group, but this is a presentation as a generalized Weyl algebra. So polynomial ring in two variables, automorphism like that, element like this, and C is a Casimir. Okay, so now we come to a new object, which existed 30 years ago, but the point is there were no examples natural. So now natural examples appeared. When we start with my former PhD student, Tao Lu, classify some prime ideals in classical algebras like Schrödinger algebra, Euclidean algebra, and also in classification of simple weight modules. So this is a big problem. Suppose you have a Lie algebra SL3 to classify simple weight modules. So, but this is a kind of 8-dimensional algebra. So when we look at the kind of 6-dimensional algebra like Schrödinger, it's possible. And this kind of algebras appear. So what's the definition? As I mentioned before, we, instead of one automorphism, we deal with two automorphisms. Okay, so let me recall the definition, what is the normal element. So when we look at the ring D, an element is called normal element if this condition holds. So it means left ideal generated by the coincide with right. So now it's similarly new definition, so-called left normal element, which is naturally appeared. That's kind of definition if you want to introduce kind of generalized Weyl algebras. If this implication, so left normal if left ideal is also a right ideal. So it means this inclusion holds. And similar story, right normal elements. Okay, so what is the generalized Weyl algebras of degree of rank 1? So we start with a ring. We start with any ring endomorphism, not necessarily automorphism. And we start with the element, with the element of D. Suppose D is a free algebra, you start with the element of the free algebra. In the previous definition, it was a central element. Here it's just arbitrary element, such that this condition holds. And this is the condition, you see, which not that easy to satisfy this condition in some sense. So it means this element is tau sigma invariant, and this element A is a left normal, because when you move arbitrary element of D to the left, it is twisted by this endomorphism, not necessarily automorphism. And similar story, sigma A is also left normal elements, because when we move elements of D to the left, they're twisted by endomorphism. So it's a left normal, but not normal, because this condition doesn't hold. Suppose sigma tau is kind of taking the value of the point at 0, say, in polynomial ring. Of course, this will be left normal, but not right normal. So what is the generalized Weyl algebra? So we start with the ring D and add two elements x and y. And the condition defined in relation precisely as in the previous case. The only difference here, we replace sigma 1 by tau. And that's it. So it means this condition, this is the theorem, are necessary and sufficient condition in order that these relations make sense. So when we look at the central element, when tau is equal to sigma 1, so this is identity. Suppose tau is equal to sigma minus 1. So this identity, sigma A equal A. So then this is identity homomorphism. So it means, this means simply A is a central element. And this is an identity, so it means this is a central element. So it means in all definitions, these conditions automatically hold. So it means they are kind of not present on the scene. But when we look at the general situation, this condition must be satisfied. You see, so suppose your element A is normal. So it means there is an inner automorphism, which regular normal element. So in fact, on the scene, we have three automorphisms, sigma, tau, and automorphism related to A. And these are relations between these three automorphisms. So it means when you look at the algebras, which has a huge group of automorphism, so these relations are not that strong, in fact, right? So basically, you have three automorphisms, but one automorphism can be replaced via other two, and two has no connection whatsoever. Okay, so you can see from the definition that this algebra is Z-graded. And these are graded components, which is a free left module over D, which is in general not a free right module. But suppose this sigma tau automorphism, it will be also free right modules. And I'm going to explain the simplicity criteria for these algebras. And let me give necessary definition in order to explain this. So suppose you have a ring, arbitrary ring, and sigma be a ring endomorphism, then ideal is sigma stable if this inclusion holds. And the ring is called sigma simple if 0 and D are the only sigma stable ideals. And endomorphism is inner if there is a unit of your ring such that sigma D is equal to this. This is a definition of. So now, theorem 2 is a simplicity criteria of generalized Weyl algebras. So these algebras surprisingly have a plenty of two-sided ideals. So roughly speaking, 4 types. And these kind of 4 conditions are excluded one of these types ideals. So that's why the problem, if you take, say, UQSL2 or Witten deformation, so this is a problem to describe kind of various sort of ideals, and this explains why it's difficult, because we have different types of ideals, right, and how they interfere with one another. So this is a problem. Okay, so So there is a general criteria, but I here give only with some additional condition that this element are right normal. Okay, then the generalized Weyl algebra is simple if and only if the following conditions are satisfied. So the elements are regular. Regular means non-zero divisor in D. So suppose if you choose A is non-regular element, this ring is not simple straight away. And this ring D is sigma simple. And sigma I is not an inner automorphism for all I. And the left ideal, which is generated by A and sigma I, A is D. So when you see here, there is no tau. But the second bunch of conditions, roughly speaking, where sigma is replaced by tau. So the elements are regular, tau is simple, here is sigma simple, tau I is not inner automorphism, and this condition holds. So it means, as I mentioned, when this sigma and tau are automorphism, they are kind of sort of independent. And this condition, it's rather strange that you see you have two different conditions which are rather independent and gives you simplicity criteria. So the point is, for that, for simplicity, this is a very strong condition on the ring. And these three conditions that define the generalized Weyl algebra guarantees that this kind of phenomena happens. And this is very useful. Suppose your sigma kind of affine automorphism, say a polynomial ring in two variables, for example, of Weyl algebra. Sigma is a sort of affine automorphism, and tau is a very complicated automorphism. So it's easy to check for affine automorphism, right, that this condition holds than for arbitrary one, because so this is kind of usefulness to have these two types of conditions. So what about the center? You see, center is sort of complicated thing. If you start to look, so we start with the generalized Weyl algebra, that the center is a z-graded subring of A. So it means if it has this structure, where D0 is simply, so you have the center, and this denotes sigma tau invariance. So what about the rest of the component? So Di, where I is greater or equal than 1. So these elements must satisfy this condition. And similar story for D minus I. So inter is in tau invariance, that satisfies this condition, B should be removed. So it means this condition means we have to look at the right normal elements, because this is precisely alpha is a right normal element, right? So that's why to find, of course, when you have a quantum groups, usually there are plenty of normal elements. But suppose when you have a Lie algebras, there are not, unless elements are not central, there are not so many normal elements. So this presumably kind of explains why the center for Lie algebras is sort of so easy. It's a kind of polynomial in classical situations. Okay, so now when we look at the involution, so let me recall that what is the involution is suppose you have a ring. So this is anti-isomorphism of degree 2. So Weyl algebra has a very nice involution, simply Fourier transform if you prefer. And when we represent the Weyl algebra, generalized Weyl algebra, so H is simply D times X. So you can easily see that this is star invariant element. And so in some sense, so the question is, suppose you have a generalized Weyl algebra, and we have the ring with involution, like in this example, we have a ring with trivial involution. So it means when you have a commutative ring, an identity map is obviously involution. So the question is, can we extend the involution to this algebra? And the answer is yes, if the star and this endomorphism satisfy these natural conditions. Then the involution can be extended in the first Weyl algebra way, simply swapping X and Y. So for example, if you have a particular case when D is commutative ring and sigma and tau are automorphism, and tau is sigma minus 1, that then the trivial evolution, where you put here star is a trivial map, so sigma tau is identity map, this is identity map, hence you have to choose, and this is also not a condition because star acts trivially on D. So it's obvious, always possible to extend trivial involution to the whole ring. So this, if you want analog of the Fourier transform for a large class of algebras. And similar story, as I mentioned, there exists generalization of this construction for arbitrary. Not we started with 2 elements, but 2n elements. Okay, so now we come to another class of ring, which is called diskew polynomial rings. And a similar story, we start with the ring, 2 endomorphisms and 2 elements of the ring, and that satisfy the natural condition. And if you deal with the kind of algebras which were kind of that you recognize presumably some of these conditions. Okay, so D is a ring, sigma and tau be ring endomorphisms, and rho and B are simply element of the D. Suppose D is your differential operator on the variety, this will be endomorphism of this ring, and rho and B will be differential operators, such that these 2 conditions hold. Then what is a diskew polynomial ring? So you add to D 2 variables, x and y, and the relations are the following, defined in relations. So 2 relations as for generalized Weyl algebras. So when we move D twisted by sigma, and y twist elements of D by tau, and the relation like that. In all these quantum groups, UQSL2 and so on, they can be represented in this fashion, but usually rho is a scalar element and B is a very special element. Here elements are arbitrary, right? Not necessarily from the center. Suppose you take a smooth algebraic variety, the center, it's a kind of algebraically close, it's a kind of very small one usually, so it's very strong restriction, but here we simply take arbitrary element. Okay, so if you want to satisfy this condition, it's a sort of, for example, when you look at element B, this is left normal, because when we move D to the left, it is twisted by this endomorphism. Of course, if you have a commutative ring, this is not a restriction, right? Since every element is a left-right normal, but suppose if you want to produce something non-trivial, then you have to look at the ring and at least you have some left normal elements or normal elements. Now we know the quantum algebras has plenty of normal elements, and that's why this construction is kind of useful in study algebra. So let me give a kind of natural example. So we have to choose ring D. So we simply choose a quantum plane. So there are kind of, now we have to choose kind of element B, right? So B should be left normal elements. No, it's obvious from the very definition, P and Q and their powers are left and right normal. So we simply choose elements like that. So then we have a natural automorphism of this ring given in this fashion. And sigma and tau are simply powers of this automorphism. And rho is an arbitrary element of the field. So when we look at this condition, kind of honestly, so roughly speaking, you started with a quantum plane, which has Gelfand-Kiel dimension 2, and you add another 2 variables. So roughly speaking, you simply double this kind of construction, and you will get kind of, I'm sure this is a new algebra, even on this very simple level. Okay, so now question, what is the relation between, so when we look at algebras like Witten, Voronovich, UQSL2, this example can be represented in this construction. So this is a particular case of the construction, and usually this kind of rings studied for the last 25 years. So you have a ring, you have an automorphism, you have an element of the center, and rho is invertible, and rho is sigma invariant. Then you have a ring which is obtained from D by adding two variables x and y that satisfy this relation where tau is sigma minus 1. So you see this condition, rho is sigma invariant and belong to the center, automatically satisfy this condition 1. So it means this condition 1 which is necessary and sufficient for the construction to exist. And many algebras mentioned before can be represented in this form. So let me look at USL2. So USL2 is generated by 3 canonical generators for SL2 Lie algebra subject to the obvious relations. Then what about presentation? So we have to choose D. So this is KH. H is a Cartan element. Now we add 2 new variables x and y. So what about the automorphism? Automorphism is a shift. So what about this element rho? It's simply 1. Now, of course, you can choose arbitrary. Since this ring is commutative, you can choose B arbitrary element, right? Rho is this is precisely what Smith done and published big paper, so-called very famous one, so-called algebras, similar to USL2. It was kind of in 90s. So this is precisely what he does. When you look in this language, so this element 2h is replaced by arbitrary polynomial. So it means, and he developed theory, algebra similarly, USL2 kind of produce results, and this kind of explained why this algebra is similar. No, because they belongs to the similar family, and you see, no, of course, this is an intuitive explanation. Of course, if you change polynomial linear can replace by non-linear, say, like in the examples, hyperelliptic curves, right? You will see the difference. Okay. So now, if you want to question what is the connection between diskew polynomial ring and generalized Weyl algebra, so the answer is diskew polynomial ring, when you put some conditions, are generalized Weyl algebras. And this is a very good statement because generalized Weyl algebra is much more easy to study that kind of object which has a flavor of differential operators. As I mentioned, when you compute calculation in differential operators are difficult because everything explodes, but for generalized Weyl algebras, everything is twisted by sigma or tau, and if x and y meets, they produce an element of the base ring. Right? So it means this, so suppose you take x squared, okay, just give you example. Easy computation, suppose you have a kind of dx, you want to compute, this is d is d dx, right? So in differential operators, you use kind of this relation, it will explode. But when we use the generalized Weyl algebra presentation, so this element is h. Hence, when you move it, it's twisted by sigma minus 1, which is h plus 1. And you have dx. No, but dx is h. So you have simply sigma minus 1 h, and that's it. So and this gives you explanation why it's much more easy to make computation for generalized Weyl algebras than for rings of differential operators, because you will have straight away the answer. Even you see that when you use differential operators, you have expression like that, differential operators degree 2 with polynomial coefficients. And here you have straight away that this is a product of two, even you can represent this differential operator as a product of two elements. Which is not that easy problem if you have a differential operator, and that's the question whether it's reducible or irreducible. And moreover, these two elements commute. So you have two different presentations. Okay, so the answer to this question is the following one. So we start with a diskew polynomial ring, and the answer, it can be represented as a generalized Weyl algebra. So if you look at the condition when rho is a unit, so it's not a big condition, because when you take the kind of ring with plenty of units, yeah, you can. Okay, then the elements are left regular elements of this ring. There is a criteria when they are left regular. So then this algebra is a generalized Weyl algebra. So it means the ring D here is a skew polynomial ring. So this is straight away generically non-commutative. So you have to add new variable h. And the endomorphism, the defining endomorphism, is the product of these two guys, which is determined on this ring. And so now what do you have to do? Sigma and tau, they are endomorphism of this D. And in this presentation, sigma and tau endomorphism of the Kelly D, which is a non-commutative ring. No, and the extension of the sigma tau are given in this kind of fashion, very similar way, sort of affine-like automorphism. And the element A is a very simple, simply H. And hence you can kind of, computation in this ring will be much more easy straight away. Okay, so now we come to the simplicity criteria. So this is a general simplicity criteria, and also there are, okay, so let me start with the general one. So E is a diskew polynomial ring, rho is a unit, and we don't know by nu is a product of these guys, and we assume this is an epimorphism. Suppose sigma and tau are automorphism, this is not a condition. So then this ring is a simple if and only if kind of the following conditions are satisfied. As I mentioned, each of these conditions simply prohibits some types of ideals. So sigma and tau are automorphisms. This ring is simple. And each natural number, there is no elements like that. So this is element D, Kelly D, which is a skew polynomial extension of this D by adding H. That satisfy the following properties, that for arbitrary element D, this condition holds, so it means this element P is a left normal. It is sort of eigenvalue with respect to automorphism. This is sort of because this is simply an element of your ring. This is not a scalar usually. And element H, P commute with H. And there is a particularly given countably many elements which are defined in the expression, very complicated, so I simply didn't include it, that these elements must be unit. So usually these elements are not unit, but, and similar condition when sigma here is replaced by tau. So because what we did, we simply applied the generalized Weyl criteria in this way, but the point is, this is not straightforward application because generalized Weyl criteria is given in terms of Kelly D. But this criteria is given instead of the original ring D. At Kelly D, this is extension of this ring. So idea is the work first to apply generalized Weyl criteria, then using it, this is the first step, and the second step, equally non-easy, to express the conditions which are given in terms of Kelly D, given in terms of the small ring D. This is not easy because this is the Ore extension. You see, it's kind of, to drop Gelfand, roughly speaking, Gelfand degree of dimension by 1, it's in your criteria. It's not easy as a rule. Okay, so when we look, so this is a general for arbitrary ring. Suppose you have arithmetic ring, there is no characteristic. But when we look at the simple ring, right, when you look at the center is automatically a field. So we have two cases, characteristic 0 and characteristic P. So now the next two results simply use this information, right? So so when we kind of apply this theorem to gives you for Q algebras, this will be the last slide, right? So it's simply specialization for Q algebras. Of course, if you're interested in simple ring, they must be other Q algebras or algebras of a ring FP, finite P. Okay, so the ring is simple if these are automorphisms. D is sigma simple. You see C consisted of 3 conditions. Here it collapses to 1 condition. And when we look at the example for USL2, this condition precisely necessary and sufficient condition for the classical Casimir exists. So it means if you want to find the Casimir, you have to solve this equation. And this element are not unit. Okay, thank you very much for your attention. Integral differential algebra, maybe it could be, but I haven't thought about that. So you see, as I mentioned, the difficulty is to satisfy these conditions at the beginning. So suppose if you're interested in diskew. So these conditions. You see, if you have 2 arbitrary endomorphisms and 2 arbitrary elements of your ring, say free algebra, and they satisfy not suppose generalized Weyl for relation. It surely, roughly speaking, if you have a commutative ring, fix 2 automorphism, 2 elements, and satisfy this relation, surely it should be conditions, right? So this, in commutative situation, it's rather easy because, as I mentioned, centrality collapses. But in non-commutative situation, it boils down to find, say, normal elements. In quantum world, there are plenty of them, but in world of Lie algebra, there are not so many. So this is presumably was the reason that's why this kind of construction didn't appear before, because simply there are no ingredients. But when we study when we look at this kind of simple Lie algebras, but when we start to look at the extension simple Lie algebras via some other algebras, no, roughly speaking, any algebra can be, when you look at the radical and de facto algebra, so radical splits, so any Lie algebra is a semi-direct product of simple or semi-simple algebra via kind of nilpotent one. Right? So when you like Schrödinger algebra, then there are these elements surprisingly appear. So this condition can be satisfied, right? So this is the reason. Simply, we didn't look at more complicated algebra because, yeah. Yeah. Thank you very much. This is a very good comment. This is precisely what appeared, say, in Schrödinger algebra. You see, when you look at this kind of central element, it's a kind of long computation. And what we did using this approach, exactly, there is a hidden SL2 structure there. And the central element, which for Schrödinger algebra, this is precisely the classical Casimir element for this hidden SL2. This is, thank you very much for your comment. Yeah.